Okay, class, here we go. Ready to get started. Announcements. Let's see. What is this? You have your test on Tuesday on boilers and turbines, potentially covering these two turbine videos, the boiler notes and this turbine stuff, the fracture stuff we talked about, the FATT, the Liberty ships breaking apart and sinking at dock. Not too much on that, but a little bit about the upper shelf, lower shelf, fracture toughness. Maybe a few questions on that. We'll be on iLearn. We'll be mostly true, false, multiple choice. And I haven't been working on it yet, so I can't give you much more in specifics, but I expect I'll keep you busy for an hour and 20 minutes. So expect that. And so you'll log into iLearn and it'll open up for you at 9:30. I'm sorry, that's the other class, at 1:30. And you'll have an hour and 20 minutes or so to do it. Okay. And then next Thursday we go to Kingston. So everybody that's going should meet at Brown Hall. I mean, I don't care if you go directly, but you got to know how to get into the plant. And I know how to get into the plant, and I suspect most of you don't. So wouldn't be a bad idea for us to kind of caravan down there. Would be better to not have everybody drive their own individual cars. It would be better to have a few people ride with somebody, so we don't show up with 10 different automobiles. I guess, I mean, the parking lot can handle it, so I don't really care. But we'll leave at 7 a.m. sharp here, because that's 8 o'clock there, and it takes every bit of an hour and 15 minutes to get down there and get in and start talking to them. Probably take more like an hour and a half before we actually start conversations in their meeting room. So we'll talk probably once we get down there about 30-40 minutes with them, and then we'll go out and walk around, and they pretty much will take us any place we want to go. This time of year, they may not be generating much power, which is fine. If they're not generating power, it's a lot quieter and you can talk. You still see the same equipment. It doesn't really matter if it's spinning or not. I hope they do have one boiler going so they can open the door and you can look in and gaze at the fireball and all that stuff. That part's a little more exciting. I've got some videos of it I can show you, and will. So that's next week, and then we'll go forward from there. You guys do have a project, a PowerPoint project that I hope you've been working on. If not, it's time to dust that puppy off and start looking at it. Okay. All right. Well, I'm going to go ahead and play some more of this. I don't know. We'll see how it goes. If it doesn't seem too relevant, I might stop it, but we'll probably play, I don't know, a good 20 minutes of this today, maybe a little bit longer. And then we'll go to the lecture. So let me get this fired up here for you.
Turbine internals and associated pipework. When we consider that the temperature of the steam entering the turbine is, say, 900 to 1000 degrees Fahrenheit, it is apparent that its effect upon the metallic components is to cause a considerable expansion. Now, if all the components were to expand at the same rate, this could be accommodated. But this ideal situation is not easy to achieve. For example, when the steam chest is charged, the inside of the vessel will rapidly reach the temperature of the steam. But because the walls of the chest are made very thick to withstand the high pressure, it may take some time for the outside of the wall to arrive at the same temperature as the inside wall. This is especially so because the outside surface is losing heat to atmosphere, even though it is well insulated. Consequently, there will be a temperature gradient between the inner and outer diameter of the steam chest. The faster we try to heat up the inner surface, the greater this differential will be. So what problem could this cause? Well, the result is that the inner surface tries to expand at a greater rate than the outer surface. This could, after many cycles, lead to cracking on the outer surface. But it does not always work that way. For example, as the inner surface tries to expand, but is restricted by the outer surface, the metal becomes compressed and may well exceed its yield point and become permanently deformed. The consequence of this is that when the steam chest cools down with the turbine offload, the metal does not return to its original state and cracks appear on this inner surface. So it is extremely important when heating steam pipework, the steam chest and the turbine itself, to make sure that we do not try to add heat too quickly. One commonly used rule of thumb states that the temperature rise of metallic components should not be allowed to exceed 500 degrees Fahrenheit per hour. That is 8 degrees Fahrenheit per minute. Another accepted limit states that the temperature differential across the walls of pipework, steam chest, and so on should not exceed 200 degrees Fahrenheit. On most modern turbines, thermocouples are embedded into metal components at various strategic points, such as the steam chest and shell inner and outer surfaces. These temperatures are usually recorded to give the operator guidance during startup. You must make sure to learn and remember the limits which are established for each of your turbines. In order to increase the output of the turbine, steam flow is increased, and this consequently adds more heat to the metallic components, causing expansion. The operator must take care not to increase steam flow or steam temperature too rapidly, as this could lead to unequal expansion of components and possible distortion. When this occurs on the rotor, it leads to an increase in eccentricity. The shaft and rotor take on a slight bow due to temperature distortion, and this is exaggerated by the centrifugal force of rotation. Eccentricity is dangerous because it results in a reduction in radial clearance between the rotating and stationary parts. The degree of eccentricity is measured and recorded at the operator's terminal or control board. In most machines, an eccentricity of 5 mil is considered very high. High eccentricity also shows up as an increase in vibration at the bearings. In actual fact, the expansion of the turbine components in the radial direction is quite small. On the other hand, the longitudinal expansion, that is in the axial direction, is considerable, perhaps 1 to 2 inches between the cold and full load condition. We have already seen how the turbine construction allows for the shell to expand axially, usually on sliding feet at the governor pedestal. Now, while this is happening, the rotor is expanding, but in the opposite direction. Remember, the high pressure end of the rotor is secured by the thrust bearing. It would be convenient if both the rotor and the shell were to expand at the same rate. But in practice, this does not happen. The reason is that the rotor is considerably lighter than the shell, and therefore it expands more rapidly. So during the initial loading of a cold machine, the rotor expands at a greater rate. And in fact, we run the risk of the rotating blades coming into contact with the next stage of stationary blades. This differential expansion must be kept within certain limits by restricting the rate of change of load on the machine. Differential expansion is measured and indicated at the operator's control panel or console. Typically, during startup, we will observe a positive differential expansion increasing continuously up to about 100 or 150 mil. We may have to restrict loading in order to keep from exceeding this level. Eventually, as the casing expands further and further, the differential will decrease and probably settle down to, say, plus 50 mil. The reverse situation occurs during a shutdown. In this case, the rotor contracts much more rapidly than the shell, and as a consequence will reduce the differential expansion and generally move into the negative zone. Normally, the manufacturer sets limits of differential expansion for both the negative and positive sides. The expansion position of the governor pedestal is also indicated. After a short overnight shutdown, it is probable that the turbine's shell will still be considerably expanded, while the rotor has contracted to provide a negative differential. This indicates that a hot start is required. Please make sure to check the manufacturer's recommendation for your particular machine. We mentioned just now that bearing vibration can be an indication of various turbine problems. These include excessive change in steam temperature or steam flow to the turbine, high eccentricity, water ingress, internal mechanical defects of the turbine, bearing defects, and a change in alignment of the bearings due to a sinking foundation or other bearing support. The vibration on each of the turbine and generator bearings is continuously monitored and recorded. It is important that the operator keep his eye on these reported levels of vibration. Any sudden change will certainly indicate the occurrence of a potential problem. For example, increased vibration on a generator bearing at a certain loading has been used to identify problems with the generator windings. Similarly, a temporary increase in turbine bearing vibration may be an indication that the operator is applying load too fast. If the magnitude of vibration on all turbine bearings steadily increases with time, it is probably an indication of wear and tear on mechanical components as the machine approaches the next overhaul period, usually every 5 years. In very general terms, the magnitude of bearing vibration should be less than 3 mil. In many machines, an alarm will be enunciated if any bearing vibration exceeds 5 mil. Most of the monitoring equipment we have discussed in this segment forms part of the turbine supervisory equipment. Commonly, this includes the following information: differential expansion, pedestal position, shaft eccentricity, vibration on all bearings, metal temperature at specific locations, turbine speed, percentage opening of control valves, and mechanical position of the shaft. Now, before we move on to talk further about monitoring equipment and turbine protection devices, let's take a break. Please switch off the tape now and review this material in your workbook.
Okay, I'll pause for a second. I had a question about whether on the test there would be any questions from the videos. And I think the general concept type questions, yes. I'm not going to get down dirty in the details of this, like in the turbine oil lube, section, the details of I don't know, all the stuff he's talked about. I can't even pull it all up right now. So if it's something that we've mentioned going through the turbine article and has been repeated here, some of this for general information about vibration stuff, I think is probably fair game. So the answer is yes, but not a tremendous number and not super detailed about, when the valves move and the pilot configuration and, pressurizing on one side and returning oil on the other side. I mean, I'm not going to get down to that level of detail with you. So if I write a question, I will consider it to be, fairly general in nature. I mean, it has to be specific enough to be a true, false, or multiple choice, but I'm not going to try to get down in the minutia because there's a tremendous amount of information in these videos. But I think you get a great appreciation for all of the things that can go wrong and all of the operational issues that the operators have to look out for and deal with on a daily basis by going through these. Okay, let's go on.
The major protective device on the steam turbine is the main steam stop valve. If it becomes necessary to stop the turbine due to an abnormal operating condition, the stop valve must be tripped closed. In the case of a reheat turbine, both the main steam stop valve and the reheat stop valve will be tripped simultaneously. We have already learned that the stop valve is closed by actuation of the pilot relay or trip relay, which drains oil pressure from the hydraulic system. There may be several trip relays located on the hydraulic system, actuated by different protection devices. Operation of any trip relay should cause the following action: closure of main steam stop valve, closure of reheat stop valve, closure of steam admission valves, positive closure of extraction line non-return valves, trip open the generator breaker, trip open the generator field circuit breaker, and activation of alarms and annunciation. So what are these hazardous conditions that are considered severe enough to automatically trip the turbine? Well, the most dangerous condition that must be avoided is that of overspeed. And this could occur in the case of a load rejection, for example. Similarly, we would get the same result if the generator breaker was tripped open by mistake when the unit was loaded to about 50% capacity. Of course, the turbine generator would immediately increase speed because at the instant of the breaker trip, a very large quantity of steam is flowing through the turbine. Under normal circumstances, the governor should be able to close the turbine control valve sufficiently to bring the speed close to normal within a few seconds. However, imagine what would happen if the governor failed to act properly, or the power piston seized, or some other defect prevented movement of the control valves. In this case, steam flow to the turbine would continue, with the result that the speed would rapidly rise to 2 or 3 times normal. In practice, the speed would not get that far because centrifugal force acting on the mechanical parts of the turbine and generator rotor would cause them to break up. Several instances have been reported of turbine blades and sectors of turbine wheels passing right through the turbine shell into the turbine room, with the potential for injury to plant staff and damage to other equipment. In order to prevent this possibility, 1 and sometimes 2 quite separate overspeed protection devices are installed and set to operate at 10% and 12% overspeed. Each protection device operates a trip relay to close the stop valve and other protective action, as already discussed. Here we see an example of a traditional mechanical overspeed device. Essentially, it consists of a bolt inserted into the shaft. As the shaft rotates, the bolt tries to fly out by centrifugal force, but this is restrained by a compression spring. The spring is carefully adjusted so that the centrifugal force does overcome the spring compression at 10% overspeed. The bolt then mechanically trips the latch, which allows the trip relay to move to the trip position, so draining off hydraulic oil and closing the stop valve. You will remember that tripping the stop valve also actuates the positive closure of non-return valves on the extraction lines. This is necessary to prevent entrained steam being drawn back into the turbine and aggravating the overspeed condition. Another common type of overspeed relay uses electrical measurement of speed and an electrical circuit to initiate operation of the trip relay through a solenoid. It is vital that these overspeed trips be checked for operation at regular intervals and the actual tripping speed be recorded. Now, this may be done when the unit is being shut down or started up. Adjustment of the setting may have to be made from time to time. This protection device is one of the most important on the turbine. On a condensing turbine, we expect the back pressure in the condenser and therefore at the turbine exhaust to be between 1 to 3 inches of mercury, depending upon the actual cooling water system. Now imagine what would happen if the back pressure started to rise, perhaps due to a large air leak into the condenser, or more likely a reduction in cooling water flow through the condenser. Now remember, as the back pressure increases, so does the density of steam at the turbine exhaust. With a back pressure of 10 inches, the density would be about 9 times greater than the density at 1 inch back pressure. This increase in density greatly increases the friction on the LP blading, which is still turning at 3,600 RPM. The result leads to overheating and possible damage to the low pressure blading. In order to prevent this situation, a vacuum trip continuously monitors the back pressure, and it is usually set to operate a trip relay when the back pressure reaches 10 inches of mercury. The monitor will sound an alarm when the back pressure reaches 5 inches mercury, so as to warn the operator to take action before a trip occurs. While we're talking about back pressure at the turbine exhaust, let's consider what would happen if during a startup we passed steam through the turbine before establishing cooling water flow through the condenser. Well, the steam entering the condenser would not condense and consequently would build up pressure eventually to such a level as to rupture the exhaust hood. In order to prevent such an occurrence, a large relief diaphragm is fitted to the exhaust hood. This is normally held in place simply by the vacuum inside the hood and atmospheric air pressure outside. As soon as the pressure inside the hood rises above atmospheric, the diaphragm opens, acting as a relief valve to prevent any damage to the exhaust hood casing. This diaphragm works quite independently of the mechanical devices and hydraulic mechanism that we have been discussing. Usually, the only attention required is to make sure that the water seal around the edge of the diaphragm is not leaking and allowing air to enter the condenser. Another important protection device that is set to trip the turbine is the thrust-bearing failure monitor. This equipment is fitted to precisely measure the position of the thrust collar in relation to its pedestal. As long as the thrust bearing on either side of the collar is operating correctly, there will be no change in the relative position of the collar, even when the turbine shell and the turbine rotor expand. If the thrust bearing were to fail, allowing axial movement of the rotor, we could run into the serious problem of contact between the rotating and stationary blades. Therefore, it is essential that at the first sign of thrust collar movement indicating failure of the thrust bearing, the trip relay be activated so as to close the stop valve and bring the turbine to a halt. Another condition which will cause the turbine stop valve to trip is loss of lube oil pressure. If lube oil is not available to provide lubrication to an operating machine, the bearings will rapidly overheat and fail, with possible disastrous consequences for other components of the turbine and generator. Lube oil is monitored continuously, and if pressure falls to 0 or a very low value, a trip relay will be actuated to trip the turbine. Note that this relay will also prevent the opening of the turbine stop valve if lube oil circulation has not already been established during startup. In the case of hydraulic oil, an alarm is usually fitted to indicate low pressure, but a trip relay is not always provided. This is because the hydraulic equipment is designed to operate in a fail-safe manner. If the hydraulic oil pressure fails, both the stop valve and control valve will be closed by spring pressure in their respective power cylinders. In addition to the protective devices mentioned, the operator has the option to trip the unit manually by operating the trip lever, which is usually located on the turbine pedestal. On most units, it is necessary for the operator to reset the trip mechanism manually at the turbine pedestal after any trip has occurred. The operator can also trip the unit remotely from the control room. This is simply a remotely operated solenoid which operates the hydraulic trip relay. This solenoid trip may also be activated by certain generator and boiler protection devices. For example, if an internal fault developed inside the generator, it would be necessary to trip the generator breaker and the field switch, and also the turbine stop valve to bring the generator to a stop as soon as possible. Similarly, if a fault on the boiler was serious enough to cause a boiler trip, then the turbine stop valve would also need to be tripped at the same time. Otherwise, we would be pulling steam and possibly water out of a shutdown boiler. Summarizing then, let's list the major protective devices that are installed on most steam turbines: main and reheat stop valves and associated hydraulic trip relays, positive closing non-return valves on extraction steam lines, overspeed trip, low vacuum trip, thrust bearing failure trip, loss of lube oil pressure trip, manual trip lever on the front pedestal, remote solenoid trip by operator push button, and generator or boiler protection intertripping. It is vital that all protection devices be tested regularly to ensure that they will actually operate when required. In some plants, the turbine generator may remain on load for many months at a time. In this case, some form of simulated test may be carried out. For example, partial operation of the overspeed trip mechanism is actuated, but actual tripping of the turbine is blocked. An extremely important test maneuver is the exercising of the turbine stop valves. The test circuit allows the stop valve to partially close and then open again. This test is performed daily in many plants, and the objective is to make sure that the stop valve does actually move and not remain frozen in the open position, as has actually occurred on some occasions. All of the protection devices in the world would be of no use whatsoever if the stop valve failed to close when commanded. For a similar reason, the positive closing non-return valves on the extraction lines are also exercised daily or at some other regular interval. Make sure that you are thoroughly familiar with the established procedures for testing protective equipment on your turbines. Also, using the information that we have presented here, make sure that you know the function and location of all protective devices on your particular turbines. And note that there are certain items of equipment that could be considered protective, but they do not actually trip the stop valve and shut down the turbine. For example, a low-pressure deloading device is often connected to the hydraulic control valve system. The objective of the deloader is to protect the turbine against falling steam pressure from the boiler. For example, a defect on the boiler auxiliary plant may reduce steam output from the boiler. But as the turbine is not aware of this, it will continue to pull the same steam flow out of the boiler, with the consequence that the pressure falls and will continue to fall as long as this condition prevails. The danger is that with falling pressure, the water level in the boiler drum will rise substantially due to swell, and this in turn may lead to carryover, that is, water passing along with the steam into the turbine. To prevent this possibility, the deloading device monitors the steam pressure. If this falls below 80% of nominal, the deloader starts to close the control valves to maintain the steam pressure at 80%. Of course, this will reduce the output of the turbine generator, but this is far preferable to damaging the turbine. During startup of the unit, which may well take place at low steam pressure, the deloading device is bypassed and only brought into service when the unit is on load and boiler pressure is normal. Most of the turbine operations are performed remotely from the central control room, with the support of regular local inspection by a roving operator. In traditional control rooms, the operator works at a large panel, which includes switching controls, indicating lights, indicating instruments, and recording charts for the complete unit, that is, boiler, turbine, generator, and auxiliaries. The annunciator panel, usually located above, provides indication of any alarm conditions. In newer plant installations, and in fact, in many converted plants, digital control systems are employed, and in this case, the operator works at a console with 3 or 4 CRTs, providing indications, alarms, and the means for remote operation. Referring to turbine operation, the indications we are most interested in are steam conditions, that is, pressure and temperature, vacuum, usually dependent upon certain water conditions, lube oil temperatures, bearing vibration, and mechanical condition of the turbine as indicated by the supervisory instruments. Now, in this module, we have only been able to cover the most common features of turbine operation. Using this information as a guide, you must make sure to thoroughly learn and become familiar with your own turbines. No doubt each of your machines will have their own idiosyncrasies, which become well known to the experienced operator. Please switch off the tape now and review this material in your workbook.
All righty. So that's the end of our turbine presentations. And we will now pivot on to some combustion fundamentals. We're not going to go terribly deep. Oh. Need the mic up, sorry. Oh. Have to move the mic around for this to work right. Okay. So we're going to move on into some of the combustion stuff that we started just briefly, I think, last time. Let me pull down. I know we've covered first part of this. We went to table 1 and looked around. That was all those combustion constants from the steam book. And then, of course, we have to define a mole, which I know you guys know what a mole is, right? It's that little furry creature that pops up in your backyard. So the number that we always remember is what? Avogadro's number, right? 6.022 times 10 to the 23rd. And that's the number of atoms in a mole. Is that a gram mole? Is that a kilogram mole? Is that a pound mole? Is that a ton mole? Or does it make any difference? I think it makes a difference. The size of the pile is going to change, whether it's a gram, mole, because like if you take carbon, what the molecular weight's 12. So a gram mole is 12 grams. A pound mole is 12 pounds. A kilogram mole is 12 kilograms. A ton mole is 12 tons. A little bit difference in the number of particles, right? So Avogadro's number is for a gram mole, because that's what you typically used in chemistry. But you just, sometime you'd be surprised that you remember the number and you remember the mole, but you don't remember the gram mole. Okay. Okay. So for example, you know, CO2 would be a carbon and an O2. So that's basically 12 plus 32 would be 44. And we can write it pounds, we can write it grams, we can write it kilograms. You know, it's basically a particle. It's a certain number of particles is basically what it's given us. Okay, let's look at table 2 here, and that's in the combustion tables over here. Okay, so these are just for combustion, common reactions. And I know my chemistry is not great. You guys are probably much better than I am at it these days. But this is pretty simple. I can probably handle this, you know, just balancing the reactions. 2 carbons plus an O2 gives 2 COs, which we really don't want to do, but we could. And so you see the molar ratios, pretty obvious. There's the masses, 2 carbons, 12 each, so 2 times 12 is 24, and 1 O2 is 32, so they add together, you get 56, conservation of mass. And then we have the heat of combustion, and this is the higher heating value that we defined last time. So, you know, again, carbon monoxide is a low-grade fuel. They're showing 3950 BTUs per pound, whereas carbon is 12,093 if you burn it to CO2. If you burn it to CO, not so good, right? Let's see, and so we can go ahead and burn 2 COs plus an oxygen to get 2 CO2s, and there in that reaction we pick up 4347. Of course, that's 2 carbon, 2 COs. Hydrogen, what a great fuel. 2 H2s plus an O2 goes to 2 waters, and we get 61,000 BTUs a pound. Pretty impressive. Of course, that's a lot of hydrogen because it's pretty light. So you get quite a few molecules, but nonetheless, on a per pound basis, 61, almost 61.1. It's a lot of energy. Sulfur, we really don't want to burn it, but it is a fuel, not a very good one, and it produces pollution. But if we burn a mole of, well, if we burn a pound of sulfur, I guess we get 3980. And then you can see methane. That's basically mostly natural gas is methane and some of the other fuels. And you see the reaction. We'll see shortly if those O2s were coming from air. For each O2, we'd have what, 3.77327 moles of nitrogen that would come in and just go through the process. It would come in cold and go out hot and carry some energy with it. But what are you going to do? The oxygen's free. You take it from the air. And if you buy a bottle, if you want just O2, you gotta buy it, and it's pretty pricey. So that's the way it goes. Okay, so that's that table 2. Molar evaluations. Gaseous fuels are usually given the analysis. If you send a sample or you want to know what a particular natural gas or some gaseous fuel is made up on, you usually get it on a % volume basis. So here's an example of a fuel gas analysis. This could easily be natural gas. And you know, every well that produces natural gas produces a little bit different mix, because you know this stuff is formed way down deep in the ground and comes out, and then from all kinds of different wells gets cleaned up a little bit, and then it enters the pipeline where it all mixes together. And so, you know, it's not exactly the same from one day to the next, from 1 month to this. I mean, it's pretty close. And your natural gas supplier for a given month, or maybe even shorter term than that, can give you some specifications on the gas that you burned last month, because the heating value will change a little bit. And, you know, it's just not the same, exactly the same product. At any rate, if you receive an analysis like this, you would see that this is methane, CH4, 85.3%, C2H6, I don't remember what that is, 12.6%, a little bit of CO2, 0.1%. That's elemental nitrogen, just N2, 1.7, and a little bit of oxygen, 0.3%. So you add it all up. And so that note down at the bottom, for an ideal gas, a volume fraction is the same thing as a mole fraction. Okay, and we'll do, this next page, we'll do a little derivation of that, but you need to realize that. So that volume fraction, I mean, it's basically a particle count fraction. Okay, so in that sample, 85.3% of the particles in the container were methane. 0.3% of the particles in the container were oxygen. That's how you can interpret that. Or another way to think about it is, if you could magically blow a whistle, say you had a box full of that gas, and so it has a certain temperature and pressure. And so if you could blow a whistle and all the oxygen segregate into its volume, partial volume, and all of the methane into its, and all the CO2 into its, then that would be the % volumes that would be occupied in the total container by that gas. And they would all be at the same pressure and temperature that the entire mixture was at. So that's kind of the partial volume concept. You can think about partial pressures where everything is at the same volume and temperature, and then each gas exerts a certain part of the total pressure. Or you can think about the gases being at the same temperature and pressure, and then each gas would segregate into its partial volume. So it's kind of like flip sides of the same general concept. Okay, so here's how we can well, define and then derive this, mole fraction. So we just want to be real clear that we understand these definitions. Mole fraction of a component in a mixture. So that could be the methane. So it's the moles of methane divided by the total moles in the mixture, okay? So the volume fraction of a component in a mixture, and this would be that partial volume concept where, we have segregated each component off to itself, and each one occupies a different volume based on how many molecules are present at the same pressure and temperature. And so the volume fraction then is the volume of that component divided by the total volume of the mixture, okay? And I've got notes up there. Make sure that I talk about, partial pressure versus partial volume and all that sort of thing, okay? Well, so since we're going to assume ideal gas behavior, so let me write over here, I've got the ideal gas law ratioed. So on the first one, I'm looking at component 1. So the pressure is the pressure in the whole container. V1 is the volume of the total container that's made up of species 1, and that's equal to the number of moles of species 1 times the universal gas constant times the temperature, okay? And then I'm going to divide that. I'm going to write the gas again, ideal gas law again for the entire mixture. So again, I have the total pressure in the container, which is common to all the gases. And then I have the total volume of the mixture or the whole container is equal to N, the number of moles of all of the gases added together times the universal gas constant times the temperature. Okay, and then look what drops out. Well, the pressure is the same, and the gas constant's the same, and the temperature is the same. So then basically that tells you that V1 over the total volume is equal to N1 over the total number of moles. And so that tells you that the volume ratio is equal to the molar ratio. And so that's pretty simple derivation. So the moles of component divided by total moles is equal to the volume of a component divided by the total volume. But that's handy for us when we go to start working problems and doing this. Okay, so this is just repeating the numbers from up here on this previous slide, but we listed them as percent by volume. Now that we've done this little derivation, we can say, well, this is the molar percent, or another way that Babcock and Wilcox likes to present this stuff is say, let's say that we just had 100 moles of the gas. Another way you can think about it, you can do 1 mole, but then you wind up writing everything's a little decimal fraction. And so it's just handier to assume you have 100. So we're going to say we have 100 moles of this gas. And so we have 85.3 moles of methane, 12.6 moles of C2H6, 0.1 moles of CO2, 1.7 moles of N2, and 0.3 moles of O2. So it all adds up to 100. And you can think of that as percent, or you can think about it as moles per 100 moles. However, it's not wrong either way. Okay, so then when we do these combustion type problems, we want to break it down instead of methane and all these other potential fuels. We want to break it down into the elements, okay, which is not hard. So we're going to do carbon first. And so we want to determine the number of moles in the methane, the CH4. Well, in 100 moles of fuel, we have 85.3 moles of CH4. So we have 85.3 moles of carbon because it's a 1-to-1 ratio. Lori had to, are you okay, Lori? Something hit the floor, I don't know. Okay, so then we got the C2H6. Well, we've got 12.6 moles of C2H6, but we're counting carbon, and so it's C2. So I got to take the 12.6 times 2, so I get 25.2 moles of carbon in the C2H6. And in the CO2, it's it's a 1-to-1 ratio, and I've got 0.1 moles per 100 moles, so that carries over, okay? So then in my 100 moles of fuel, I've got 110.6 moles of carbon, which then I'm going to go burn here in a minute, okay? So now let's count the hydrogen. Similar process. I'm going to count, I could count H's, but in this I'm counting H2s. I don't know why. I guess that's because what the Babcock and Wilcox book did. You could count H's. You just got to, do it correctly. But we're counting H2s. So I've got 85.3 moles of methane, and the formula for methane is H4. So I got to multiply the 85.3 times 2 to get the number of H2s. And so that's 170.6 moles of H2 in the methane. So likewise for the C2H6, it's 12.6 moles of C2H6. And so I'm counting H2, so I got to multiply by 3. And so that's 37.8. And that's all the hydrogen that I have. So I add that up and I get 208.4 moles of hydrogen per 100 moles of fuel. And then oxygen, not much. I've got a little bit tied up in the CO. It's 0.1, and it's a 1-to-1 ratio because I'm counting O2s. And so I've got 0.1 moles of O2 in the CO2. And then I have a little bit of oxygen. I have 0.3 moles of just O2. And so that, I bring that over. And so I add those together and I got 0.4 moles of O2 per 100 moles of fuel. Okay. Then I've got my nitrogen N2, and that just, that's what's in that gaseous fuel is 1.7 moles of N2 per 100 moles of fuel. So I write that down. Okay. So now the bullet here says we could go back to table 1, which is all of the combustion constants, and easily determine the oxygen air requirements and products of combustion. I think we can probably do it without going back there. So let's see if we can't avoid going back and looking. Let's take a look as we move through this. So, so this is just summarizing all of that data that we just generated on the elemental content of our 100 moles of fuel. And then we're going to convert from moles per 100 moles to pounds per 100 pounds of gas, because we've got to be comfortable with moving back and forth from the world of moles and molar ratios to mass and mass ratios. Okay, so we're just going to illustrate that. So we start out with carbon, and we had 110.6 moles of carbon per 100 moles of fuel. And so the molecular weight of carbon is 12.011 according to the steam book, and that's pounds. I'm going to work in pounds. You could work in grams. You could work in kilograms, whatever floats your boat. So each mole is 12.011. So if I just multiply those together, I get 1,328.1 pounds of carbon per 100 moles of fuel. Okay, it's important to go ahead and write these units out. The units will really carry you through. So we're going to go down through all of the fuels and do that same arithmetic. So the hydrogen, 208.4 moles per 100 moles of fuel, times molecular weight, 2.016. So we get 420.1 pounds of hydrogen per 100 moles of fuel. O2, I've got, comes out 12.8 pounds. And then nitrogen is 47.6 pounds per 100 moles of fuel. So if I add all that up, I get 1,808.9 pounds per 100 moles of fuel. And then if I come and I take each one and I divide by this total, then see, this is total mass per 100 moles. This is mass of carbon per 100 moles. And so this then will give me the pounds per 100 pounds, or I can consider that the percent. Either way you want to. So then I have converted from moles per 100 moles or percent moles to percent pounds. Okay, and so the conversion back and forth, pretty simple, is just the molecular weight. So if I'm going from moles to pounds, I multiply it by molecular weight. If I was going from pounds back to moles, I would divide by the molecular weight. So the molecular weight is what transports you back and forth from the world of mass to the world of moles and back and forth. Okay, very good. Okay, an ultimate analysis. And this is where you get the elemental breakdown of the fuels. Well, not necessarily the elemental breakdown. If it's coal, you will. If it's a gaseous fuel, you may well get the gaseous components back. But anyway, there is approximate analysis that gives you far less information. It doesn't give you the carbon and the hydrogen and all that sort of thing. It just gives you the fixed carbon and combustibles and stuff like that. But so when you send a sample out for a fuel analysis, you want to request an ultimate analysis if you're going to really do any calculations with it. Okay, the ultimate analysis is determined on a percent mass basis. And that would be for a coal, or a solid wood. You can get an ultimate analysis on wood or a solid based fuel. So then to convert to molar basis, then like we said, we just divide by the molecular weight, and that's what this is showing. Pounds of constituent per 100 pounds of fuel, and then the molecular weight is the pounds of constituent per mole on a molar basis, the pounds per unit mole, and then so when you do that arithmetic, you get moles of the constituent per 100 pounds of fuel. Okay, table 3, let's go look at table 3 here. Yeah. All right. So this is starting to get into it a little bit. So let's say we sampled the coal pile, and there actually is an ASTM standard on how to sample a coal pile. You think, oh, just go take your shovel and pick up a couple of, get a shovel full, throw it in a bucket, send it to the lab. No. You got to take some from here, and you got to get up so high, and you got to do this, and you got to do that if you're going to do it according to the ASTM standard. Now, how much difference it makes, I don't know, but I do know there's an ASTM standard on how to select the coal out of a big pile that you're going to send to the lab. Okay, so this is what comes back. So this is your ultimate analysis that comes back from the laboratory. We see on this analysis 72% carbon. Hydrogen, H2 hydrogen, 4.4%, sulfur 1.6, pretty low sulfur. High sulfur coals, 3-4%. And they're pretty cheap. Low sulfur coals, even lower than this, pretty expensive. Because that's one way a lot of plants try to keep down their sulfur emissions is by buying low sulfur coal. So if you own a coal mine that's sitting on the low sulfur seam, you're going to make more money than if you own the coal mine that's sitting on the high sulfur seam. Now, these days, a lot of the utilities have scrubbers and equipment to clean it up because they've ratcheted the levels down so low. So, but still, I know when Tennessee Tech, we've been off coal at about 3 years. We used to burn coal over there. And Tennessee Tech would pay, they were paying probably pushing $140, $150 a ton for coal. TVA, who had scrubbers, was buying, not so good a coal and cleaning it up, cleaning up their emissions. They were probably paying, I don't know, $70, $80, $90 a ton. So, but Tech didn't have any sulfur cleanup. So the only way Tech could limit the sulfur emissions was to not put any sulfur in the boiler. Okay, so we get oxygen, 3.6, nitrogen, that's elemental nitrogen, 1.4, water, and then ash, 9%, which is like rocks and stuff that is not going to combust. It's just going to, go through the system and fall out. Might take a little heat with it when it goes, so it could have an efficiency penalty associated with it. So we list the percentages, or you can think of it as pounds per 100 pounds, however you want to think about it. And then the molecular weight, just list it. And so now we're going from mass to molar, because we're going to do our combustion analysis on a molar basis. So we're going to divide. So 72 divided by 12.011 is 5.995. And then we can go up and check the reaction, but we know if we burn this properly, and we're going to assume at this point that we burn it properly, right? So we're going to get CO2. So it's a 1-to-1. Every carbon produces a CO2. So the combustion product is CO2. And so then we have moles of theoretical O2 required. Now, so that last column, we're going to add up and determine our stoichiometric oxygen. If we had perfect mixing, that's what we would have to put in, okay? Because every little carbon would find its intended O2, and they would do great oxidation together and create a CO2. It's such a romantic story, and everybody matches up perfectly. It's fairy tale land. Okay. But anyway, so to burn 5.995 moles of carbon into into CO2, we need 5.995 moles of oxygen, of O2. Okay. So then the hydrogen, same deal, divide by molecular weight, 2.016. So then moles of H2 per 100 moles of fuel is 2.183. It's going to combust into water vapor. Water, and then it depends on whether we condense it or not after we create it. And then so it's a 2-to-1. We're counting O2, so we're going to need a half of an O2 for every H2. And so we got to take the 2.183 and divide by 2. So we get 1.091 as the oxygen requirement. Sulfur, same deal, 0.05 moles per 100 pounds of fuel, and it's a 1-to-1 with oxygen, and so we need 0.05 moles of O2 to combust it. The O2 is present. It's 3.6%. We divide by 31.999 and we get 0.113, and we get a credit because that's oxygen that's in the system that's provided by the fuel. And we assume that that oxygen is available to support combustion. So that's what the parentheses mean. It's a negative. We get a credit for it. The nitrogen doesn't do anything as far as oxygen is concerned. The water vapor that's in the fuel, probably it may be liquid. It could be, and it may go up as a vapor. It's an energy loss, but it doesn't combust. And the ash would basically just drop out because it just floats through it kind of falls out at some point. Okay, so if we total that up, well, our ultimate analysis got us 100%, and then our moles of different elements per 100 moles of fuel is 8.835. And we see all our combustion products, and then our moles theoretical O2 required, 7.023. Okay, so that's the stoichiometric oxygen. Okay, questions on that? Pretty straightforward. Let's see, let's go back to the notes and see what we're doing here. Okay, there's a note just that oxygen in the fuel is a credit. Okay, so we've got, there's another table. This one was short, so I just wrote it. Composition of air, US standard atmosphere, oxygen, 20.947%, or you could say that's moles per mole, or it could be 20.947 moles per 100 moles. However, this one is just the flat fraction, the way it's written, because it adds up to 1. N2, and this is elemental nitrogen, 70.78086, and argon 0.00934, and CO2 0.00033. I don't know if this has been revised. I haven't looked in the book. I mean, these notes were written a while ago. I don't know if they've revised the CO2 or not, or if they just leave it there in the standard, because CO2 levels have risen some. It's not going to make much difference as far as these types of calculations are concerned. The average molecular weight, 28.97965. You see it 966, 965. But you should probably know that number. 28.97 is fine, something like that. But that's the average molecular weight of dry air. Of course, there's no, there is going to be water vapor present, but we haven't shown that. So this is composition of dry air. I guess that should be pretty obvious. Okay, so here's our discussion about atmospheric nitrogen. To simplify calculations, N2 is considered to include argon and other trace elements. And so that's where we write this capital N2A. When you see the A, you know that that includes argon and CO2 and any trace gases in there. And it bumps the molecular weight a small amount. N2 elemental is 28.013 molecular weight, and N2A is 28.161. And so, it includes the nitrogen plus those other gases. So you got a little bit more stuff there. Okay, so that's what atmospheric nitrogen is all about. Okay, so air contains some moisture. Living in Tennessee, boy, we know that. As standard practice. Okay, so if you don't know a moisture level, or you're not given a particular condition of outside air, if you just have to grab one, the American Boiler Manufacturers Association, as standard practice, considers moisture content of typical air, I don't know why they do this, but they do, to be 0.013, and that's pounds of water vapor per pound of dry air. So that's kind of, if you're not given any other guidance and you need a moisture level for air that's going into a boiler or something, you use 0.013 pounds of water vapor per pound of dry air. Now, why they pay, I don't know. It's just the way it is. Okay, now, if you look on a psych chart, which, God, you know how I love looking on psych charts. It just makes my day. Here's the old psychometric chart. Okay, so you can see right here, this line, that's 0.013, right? 0.012, 0.014, so it's right there. So that moisture level is really any place on that line is that same moisture level. I think he makes a comment that it's someplace at 80 and 60% roughly. I don't know, you can look and see, it's up there. Can't hardly see these things. It's that one, that's, yeah, so that's pretty close. Not exact, but that cursor is sitting on 80 degrees at that moisture level. It looks like the relative humidity is maybe like 59% or something like that, but it's roughly there. So that's where they have taken that number. Now, if I was to give you a homework, I'll give you a psych chart, man, and I'll say, hey, your outside air is 100 degrees and 30%. So you got to come over here 100 degrees, 30%, and read your number over here. I mean, it's easy, but I want you to know where to go to get this number. And of course, this is an atmospheric pressure psych chart. So if you were in Denver, Colorado, you should probably get a 5,000 foot psych chart, and the number will be a little bit different. Okay, so there is that, or you could calculate it given a given condition. We'll see some equations here in just a second. You probably already know them. But anyway, so if I gave you, let's say I gave you 100 degrees and 40%. Well, now let's go. Can I get to 50? There's 50. There's 50 and 100 right there. Oh, that's a good one. That's right on the line, pretty close. So then that number is 0.021, because there's 0.020, there's 0.022, so that's 0.021 pounds of water vapor per pound of dry air. So you just use it instead of 0.013. If you don't have a number, then you assume 0.013. Okay, let's go back. Okay, now when we do the analysis, we need to convert from pounds of water vapor per pound of dry air to moles of water vapor per mole of dry air. And I wrote it down below, but I wrote it a little bit neater here. So here's the conversion. Here's converting the standard number, 0.013. And you can see that's pounds mass of H2O vapor per pound of dry air. That's how it's given. And what we do, we multiply by the molecular weight of dry air and divide by the molecular weight of water. Pretty simple conversion factor. And this shows you the 28.97 is pounds of dry air per pound mole of dry air. And then you divide by 18.016, and that's pounds mass water vapor per pound mole of water vapor. And so when you do that, it converts. So the standard number in terms of molar analysis, pound mole water vapor per pound mole of dry air, and it'll be the same whether it's kilograms or grams or whatever. I mean, the ratio will be the same. You'll wind up with the same number, or just whatever mass unit you want to use. So this 0.013 turns into 0.0209. And that's actually the number that we're going to use in calculations, the 0.0209. So if I give you some weird condition on the psych chart, you just go find the number that's analogous to 0.013 and then multiply by 28.97, divide by 18.016, and you've converted it. And then that's the number that you'll actually use. Okay, and so that conversion factor, when you just ratio the molecular weights, is 1.608. So if you write that down someplace, then you just take the 0.013 times 1.608 and you got it. That does the conversion for you. Okay, we good? All right, we are starting to have real fun now. And that's what this stuff in here is kind of messy, so I redid it. Okay, so that just shows the conversion. Okay, let's look at table. Did I look at table 3, table 4? Let me see. Let's see. Let's go back to the tables here. This is table 5. Yeah, this table 4 is not much. That's this composition. It's kind of hard to see there, but so air composition. Let's see, composition of dry air. So oxygen is 20.95% by volume and 23.14 by weight. And N2A, just boiling this down to two components, either oxygen or N2A, 79.05% by volume and 76.86% by weight. Okay, let's rotate this. This is kind of how we go through it. We'll quit after this. Okay, and so we're pulling these numbers from our table 3, which we just went through. So the theoretical combustion, or the stoichiometric oxygen from table 3 was 7.023. I'd go back up, but I got to rotate it again, and that's pretty obnoxious. So trust me, you can check it. Okay, then from table 4 that we just looked at in my notes, the molar fraction of O2 in dry air is 20.95%. And so you can, if I take this 7.023 and divide by 20.95, or if you just take 1 over this number, you get 4.77327. 4.77, that should be a familiar number to you, because that's the number of moles of dry air you have to bring in to get 1 mole of oxygen, right? So you can multiply by 4.77327, or you can divide by 0.2095. It's the same thing. It's just dividing by the fraction versus inverting it and multiplying, okay? So this is then, this is the stoichiometric, or the theoretical dry combustion air. So this much air contains exactly this much oxygen, and that's enough for perfect combustion, okay? Now, in this little example, we're going to assume 20% excess, because guess what? We don't have perfect mixing. So we're going to have to bring in some more in order to support the combustion process. So we want an extra 20% of this 33.523, okay? So I take 20% of it, and that's an additional 6.705, and that's what? Moles of air per 100 pounds of fuel, okay? So then my total air, my total dry combustion air is the 33.523 plus the 6.705. So this is the amount of air that I have to bring in, and that's just the dry portion of it, okay? So I got to bring in 40.228. Okay, okay, so this is the molar fraction. This is the amount of water vapor. When I bring in that air, guess what? It's not dry. And so this is my standard amount of moisture, right? That's what we just calculated. That was the 0.013 times the molecular weight ratio. And so that's 0.0209. So when I multiply these two together, this gives me the water that's in the dry air that's coming in, okay? And so I'm going to get 0.841 moles of water vapor per 100 pounds of fuel into my combustion process from the outside air. That's not all the water. That's just the part that comes in with the outside air. Okay. Now, let's see. So then the molar fraction of N2A in standard air is 79.7905, right? Okay. And so 79.5, and he's multiplying, let's see, let's go. What's he doing? He's doing theoretical. Let me go back up so we can see all the numbers. Okay. So let's see. So he's doing this 79% of line 3. Line 3 is just the theoretical air. So he's going to calculate it separately. So this is the N2A in the theoretical air. Okay. And then he's going to calculate the N2A in the dry excess air, right? So that's line 4 times line 8. So this is the excess air amount, the 6.705. And so that's 5.3. And then the O2 in the dry excess air is line 2 times, okay. So Line 2 is just, when you bring in dry air, 20.95% of it is oxygen. The rest of it's N2A. Times line 4 is the amount of excess air. So 20.95% of this is oxygen. And that's the excess oxygen that's going to come in. And it's not going to do anything. It's just there to make sure that there's enough around so that everything will burn. And then that excess is going up the stack. And it's part of the flue gas. So that's why when we do a boiler analysis, when we want to know how much excess air, we take our analyzer and we stick it in the flue gas and we measure how much is in there. And then we can determine from that percent, from that volume percent, we can turn that back into an excess air amount. Okay. All right. I think, let's see. Okay, here's his note on the moisture number. Standard combustion air, 80 degrees Fahrenheit, 60% relative humidity. There's the 0.013 pounds of water vapor per pound of dry air, which converts over to 0.0209 moles of water vapor per mole of dry air. So we did that up above. Okay, we'll stop there and we'll cut off on this. And so you guys study, and I hope everybody does well on the test. If you have any questions, let me know, email me, and that test will be open from 1:30 until probably about 3 on Tuesday. Okay, have a great weekend.